Hi, Year 11. Let's look at your multiple choice paper here. So you had 45 minutes. This is a tight paper. Now, you will notice that at the front of this paper it says take the weight of 1 kilograms to be 9.81. So G was 9.8 on this paper rather than 10. This is quite unusual, but I guess it's something to be aware of. I'm going to do a clarification with CIE, but what I want you to make sure that you do before you get to starting your papers for real in May, I want you to check this set of instructions very carefully so that if you see this, you remember to use G as 9.8. Okay, so in question 1, the speed time graph shows the motion of an object. How far, which is a distance, does the object travel at a constant speed? So, while at a constant speed, I'm looking at this section. So when I have a flat line on my constant y value, okay? So I'm only interested in this section between 5 and 15 seconds. Distance from a speed time graph comes from the area under the graph. So I just need the area under the graph while I have a constant speed. Okay, so I go from 5 to 15, that's 10. And then obviously that's 0 to 5, so that's 5. So I have 50 meters, and that gets me B. In 2, which statement about a falling object accelerating close to Earth's surface is correct? So it says in A, the weight of the object is increasing and the force of air resistance on the object is decreasing. No, so weight is constant, but we know that air resistance increases as velocity of the object falling increases because you're falling through more air particles per second. In B, the weight of the object and the force of air resistance on the object are of equal magnitude but act in opposite directions. No, well, if they had equal magnitude, the resultant force would be 0, and so there wouldn't be any acceleration, and we know that the object is accelerating, so it's not B. C, the weight of the object is constant, but the force of air resistance on the object is increasing. Yes, this is true, we know this. D, let's just check why this is wrong. The weight of the object is less than the force of air resistance. That doesn't make sense. If air resistance is larger than the weight, the up force is bigger than the down force. We would actually be decelerating towards Earth. But we know that actually what happens is once air resistance matches the weight, we reach terminal velocity. So in question 3, we've got a vector diagram. An aircraft is moving 60 meters per second in a northerly direction. Draw it out for yourself. When a crosswind from the east starts to blow. The east is over on this side, so from the east means it's coming over this way. What is the magnitude of the aircraft's velocity when the wind is blowing? Now, even if you got your direction mixed up and you went to the right, it will give you the same magnitude, so it's fine. So we know that we have 60 vertically, 13 horizontally. This is a right-angled triangle, okay? We know that if we do top to tail, so 60 and then 13, if we close that triangle, the length of that side of the triangle is my resultant. Okay, that's the overall impact of these two things, and that will be what the aircraft is doing. That will be the aircraft's velocity. So then it's just a case of a squared plus b squared equals c squared from maths. You could also do a scale diagram if you need to in the exam, but this is the simplest way. So you've got 60 squared plus 13 squared has to equal this length squared. I can find c that way, and I get 61.3 meters per second, giving me C. Okay, in question 4, an object in a space probe above the Earth weighs 3.5 newtons, that's a W value, label it for yourself. The gravitational field strength at the height of the space probe is 7 newtons per kilogram, so that tells me that G is 7 when we are in space. The gravitational field strength on Earth is 9.8, so that's G but on Earth. What are the mass and the weight of the object on the Earth's surface? We know that the mass of an object is constant everywhere in the universe. It's how much matter belongs inside of that object in kilograms. We know that weight is calculated by the mass multiplied by G when you are at that position in space. So I can find the mass because I actually know the weight value for a given G value. I have 3.5 newtons when G is 7. So that gives me my mass is 0.5, so I can get rid of C and D. I then can go back and say, well, weight is equal to mass times gravity, and I now know the mass is 0.5. G on Earth is 9.8, and when I multiply those two together, I get my 4.9 newtons. In question 5, a cyclist is travelling in a straight line along a horizontal road at a constant speed. They are telling you this because if something is at a constant speed, it is not accelerating. This means that the resultant force on the cyclist has to be 0 newtons. A constant driving force acts on the cyclist in the forward direction. Which statement about the magnitude of the frictional forces is correct? Well, we know that we have to have a resultant of 0. So if we have F to the left, we have to have F to the right. That's going to be equal in magnitude to F. That's the only way we're going to end up with a resultant force of 0 and therefore no acceleration. Oh, sorry, blue was not the colour to use. Fingers crossed I didn't use it too much in this paper. A spring has an unstretched length of 3 centimetres. When a force of 60 newtons is applied to the spring, its length increases to 5 centimetres. The limit of proportionality is not exceeded. What is the spring constant of the spring? Well, we know from Hooke's law, F is equal to Kx, where K is the spring constant that we're trying to find, F is the force applied, and X is the extension. If unstretched it was 3 centimetres and then the force causes it to be 5 centimetres, the extension is 2 centimetres. I rearrange my Hooke's law equation and say that spring constant is the force per extension. I needed 60 newtons for 2 centimetres of extension, and 60 over 2 means I needed 30 newtons for every centimetre of stretch, giving me D. In question 7, research is being carried out to produce electrical energy from the fusion of hydrogen nuclei. Now, you know from our lessons that fusion happens in the sun. This is a big clue. The sun is very hot, okay? So we know we're going to need a very high temperature needed for fusion. So that gets rid of A or B. Which row shows the two of the problems in designing a fusion reactor? So the first thing is, we need a very high temperature to be produced. That's quite difficult to do. And secondly, we know that hydrogen nuclei are 1 proton. So we have 2 protons that need to come together and combine. But we know that like charges repel because they're both positively charged. So that gives us D. In 8, the engine of a motor vehicle develops a large power. Write yourself the definition. Power is energy transferred per time taken. Okay. Which statement is correct? Well, clearly, to have a large power, this fraction needs to be very big. I need a very large amount of energy for a given amount of time in order to have a large power. That's just a recall question. That's C. Number 9 was a little trickier. The diagram shows 4 beams, each of negligible weight and freely pivoted, so it can spin around its pivot. Now, which beam is not in equilibrium? We know when in equilibrium it's balanced, it's not turning, so if it's not, it has to be turning. We must have a resultant moment. So in each one, I've calculated for you the clockwise moment around the pivot and the anti-clockwise moment. We know that a moment comes from a force multiplied by its perpendicular distance to the pivot. So we have 6 times 1 and 3 times 2. 6 and 6 balance. This is in equilibrium, so this is an incorrect choice. Again, 6 times 2 equals 6 times 2. No resultant moment. We're in equilibrium. Incorrect. In C, we've got 3 times 2 is 6 in the clockwise direction, but we have 3 times 1 is 3 in the anti-clockwise direction. We have 3 more in the clockwise direction, so this is a resultant moment. We are not in equilibrium. It is C. For those of you that picked D, I think you probably forgot that you need to find the total distance to the force. So we had 4 times 2 in the anti-clockwise direction, but we had the sum of 4 times 1 plus 2 times 2. The distance from the 2 force to the pivot is 2 meters. Okay, that's 8 and 8 in total. There's no resultant moment there. In question 10, an object of mass 1.2 kilograms is moving with a velocity 2 meters per second. It is acted upon by a force of 4 newtons. The velocity of the object increases to 5 meters per second in the same direction. For which period of time does the force act on the object? So we know that we have the impulse equation, which is change in momentum, but we also know that that's equal to force times time. Because we can work out the change in momentum and we know the force, we are able to find the time. So change in momentum is mv minus mu, which I can factorize as m brackets v take q. I know that that impulse is also equal to force multiplied by time. Now, to get time by itself in this equation, I have to divide both sides by force. So I've got mv take u over f is the time. I now have all the variables I need. The mass was given, the change in velocity was given, the force was given, and I end up with 0.9 seconds. In 11, we had to work backwards. A woman of mass 50 kilograms has 81 joules of kinetic energy. Label again for yourself with the letters so that you pick the right equation. What is her speed? Well, KE is a half mv squared. Substitute in. KE we're told is 81. M we're told is 50. The only unknown here is v squared. Okay, a half times 50 is 25. So v squared is 81 over 25. This is not the final answer. This is v squared. We have to square root to get to 1.8 meters per second. In question 12, a dam holds water in a reservoir. The height is 15 meters. So to go from the top to the bottom of that water, you're going through a height of 15 meters. The density of the water is 1,000 kilograms per meter cubed. What is the pressure at the bottom of the dam? Well, the pressure is given by rho g delta h. We know that rho is the density is 1,000, g is 10, h is my 15 meters. It gets me 150,000 pascals. Even if you chose to use g as 9.8, you will still get, with rounding to here, because it's order of magnitude that matters. Okay, in question 13, a student uses a microscope to observe pollen. This is Brownian motion. We saw this moving on the surface of water. Which statement describes the reason for this movement? So remember, we have pollen or smoke particles suspended in a liquid. The pollen and the smoke particles are really large in comparison to the liquid or gas molecules that they're in. So we can see the pollen, but we can't see the individual water molecules. But we know that what's actually happening is there are collisions between the water molecules and the pollen particles, which causes the pollen particle to start changing direction with every collision, and you get that random path change. So that gives you C. 14 again is recall. Which statement about evaporation of water are correct? Evaporation causes the remaining liquid to cool. Yes, we know that during evaporation, and actually this is explained by 2, the more energetic particles from the surface do escape the liquid. Okay, the particles that have enough kinetic energy that can leave the surface of the water in the form of water vapor, they're taking away that high kinetic energy value. So on average, the kinetic energy of the molecules left behind is lower. Temperature is a measure of the average kinetic energy of the particles. So if it's a lower average kinetic energy, it's a lower temperature. It cools things down. So 1 and 2 are correct. The only one that's wrong is 3, because 100 degrees Celsius is the boiling point. That's the fastest rate at which that change of state can happen. But evaporation is just change of state at any temperature. In question 15, again, kind of recall with your diagrams. The diagram shows graphs of displacement against time for 4 waves. All the graphs are drawn to the same scale. Which wave has the largest amplitude and the highest frequency? So amplitude is your distance from the equilibrium position to your maximum displacement. So it's your height of your wave, essentially. So you're going to pick A or B there. And then frequency is how many waves pass a point per second. So we would have, within 1 second, we would have more waves fit in. So the closer and more bunched the waves are, the higher the frequency. So we've got high frequency here, low frequency here. So you can see that A is the right choice for frequency. In question 16, the diagram shows a ray of light entering a glass block. Which calculation gives the refractive index of the glass? We take Snell's law. N1 sine theta 1 equals N2 sine theta 2. We know that the refractive index of air is 1. So on the outside, we've got 1 times sine of the angle of incidence. Some people did not spot your angle of incidence is always between the normal line and the incoming ray. So you needed to check that it was 40 and not 50. So I think a lot of you probably picked C rather than A there, but then it's just rearranging and you end up with A. In question 17, an object O is placed at a point P near to a thin converging lens. The diagram shows 3 rays from the top of O passing through the lens. So they even gift you what the rays will do. So we know that coming in parallel to the principal axis comes out through the focal point. Going through the centre, it continues through the centre. So it says the object is moved to point Q. What type of image is produced when the object is at point Q? So if you didn't read carefully enough, you probably just looked at this image and compared it to O. But it's saying, if I move this over to Q, what will the image be like? So I redraw over the top, if I can't just remember what happens. But as I bring it closer in, it's still inverted, but it gets larger and larger. And I've even measured it out to show you. So it's inverted and enlarged when the object is at Q. In question 18, a 100-meter race is started by firing a gun. The gun makes a bang, that is sound, and a puff of smoke, which we see because of light, at the same time. So this is a comparison of the speed of sound to the speed of light. We know those values, so I've listed those there for you. When does the finishing judge see the smoke and where does he hear the bang? Now we know that the speed of light is ridiculously quickly. And so light is going to travel 100 meters in such a ridiculously small amount of time. We see it instantly, okay, because we are only 100 meters away and the light is going to travel that distance faster than our brains can even realize. So we see that immediately. The bang doesn't happen quite as quickly because the sound takes longer to travel. It's only traveling at 340 meters per second. We take our speed as distance over time equation, rearrange for time. We know that it has to travel a distance of 100 meters in 340 meters per second speed. Takes about 0.29 seconds, so about 0.3 seconds for that sound to reach our ears. So the bang happens later. That's B. In number 19, a student is investigating a resistance wire. She measures the current in a 50 centimetre length of resistance wire. She repeats it for a 100 centimetre length, so we've doubled the length. What is the effect of this change on the current in the circuit and on the resistance? Work backwards. Do resistance first. We know that resistance is proportional to length. So if the length increases, resistance increases. So we can get rid of A and C. We know that the power supply hasn't changed. We can work out the current because current is voltage divided by resistance. If V stays the same, but the R value on the bottom of the fraction has got bigger, then the current value is going to decrease. It also just makes sense. If you've got more resistance, current is going to drop. In question 20, which combination of the current I in a resistor and the time T for which it results in a charge of 240 coulombs Q passing through the resistor? Label it up because it very quickly shows you need to use Q is I times T. Remember, it sounds like quit. So you can see that in A, Q is equal to I times T. 2 multiplied by 120 gives you 240 coulombs. There is no need to carry on. A is correct, but I've proven to you that the others are wrong underneath if you're interested. In 21, this is probably one of the harder questions on the paper and takes a lot longer than the others. two resistors R1 and R2 are connected in series in a circuit as shown. So we know that the current is the same everywhere in a series circle. The current is going to be equal to the voltage supplied divided by the total resistance of the circuit. So I0 can be found by V over the sum of the two resistors, because that is your total resistance in series. The current in the resistors is I0, but then another resistor R3 is then connected in parallel with R2. You should remember as a fact that when we add more resistors in parallel, we actually decrease the total resistance of the circuit, because we are providing another pathway for the electrons to travel across the circuit. So you have more charges passing a point per second, the total resistance decreases. So the voltage supply has not changed, but because the total resistance of the circuit will now be smaller, we now have the new current, I1 is V over the R total. This is over a smaller number. I now have a larger current than I did before, which also makes sense because we have multiple pathways with charges passing through both at the same time. The total current is going to be greater. I also know that I1 will be equal to the sum of I2 plus I3, which I've labelled as going through R3. How do the currents I1 and I2 in the resistors R1 and R2 compare to the original current? Well, firstly, the simplest thing to say is we know that because we've provided more pathways for electrons to travel, we have more electrons passing a point per second in total. The total resistance went down, and so I1 is going to be greater than I0. The current in I2, it should be fairly logical. We know that whatever current we have has to get split into R2 and R3. And so I1 plus equals I2 plus I3 means that I2 is I1 minus I3. Okay, and we know that I1 is bigger than I0. So we know that this value is going to be that I2 is going to be smaller than the original value, giving us D. In 22, a thin metal foil is placed in a vacuum. This tells us it's alpha particles, Rutherford's alpha scattering experiment. So we have alpha particles fired at the foil. Most go through, all the way through, undeflected, reach the other side. A very small proportion of the alpha particles are deflected through large angles. So it's the fact that it's a small proportion of them and what they're doing. What does this provide evidence for? Well, if they're deflected through large angles, it means that they've hit something and been knocked off their course significantly. They must have collided with something very heavy to rebound. Turns out that's the nucleus. The fact that it's only a very small proportion of them means that it doesn't happen very often, which suggests that hitting whatever this is doesn't happen very often, means that it's probably not very big. It's heavy in mass, but its volume that it takes up is very small, which means that it's statistically unlikely to collide with many of the alpha particles. This is that there is a tiny nucleus. In 23, the table compares alpha, beta, and gamma. Alpha is 2 protons and 2 neutrons. Beta is an electron. Gamma is wave. It's literally radiation. So, which row is correct? Even if you've forgotten the ionizing properties, you just have to remember which are which. A beta particle is an electron. A gamma radiation is electromagnetic radiation. The only one that can possibly be is C. But it is correct that alpha is the most ionizing. In 24, a student investigates 4 different radioactive isotopes. The student places a detector near each radioactive material. The background rate is 36 counts per minute. The table shows the detector readings at the start and after 8 hours. Which isotope has a half-life of 4 hours? So we know that this process occurred for 8 hours. So if the half-life we're looking for is 4 hours, then we know that in 8 hours, 2 half-lives will have occurred. So we have a source, okay? We have a detector, but the trouble is we also have some background radiation that's always at play. This background never changes, it's always 36, but this source its activity is dropping, okay? So it won't be decaying as quickly as time goes on. So step 1 is to remove the background radiation value to find the count rate of the source. So we've got in A, although the detector was reading 150 counts per minute, 36 of those came from the background, so the source was only at 114. After one half-life, this would half to 57. After the second half-life, that would be at 28.5. But the detector would be getting 28.5 from the source plus the 36 that it was always receiving from the background. And so it would be at 64.5. So we wouldn't expect to see 36. So this is wrong. For B, again, it's the same process. The detector received 212. 36 of those were background, which meant that only 176 were from the source. After the first half-life of 4 hours, that should drop to 88. After the second, that should drop to 44. But the detector won't just read the 44, it will read 44 plus the background 36, which is 80, so we shouldn't expect to see 53. In C, 260 is what's being received. 36 of those are from the background. That means that the source was providing 224. After 4 hours, one half-life, that would have dropped to 112. After the second half-life, this would have halved again to 56. But the detector would receive 56 from the source, plus the background 36. So the detector would be reading 92, which it was, so this must be the correct one. In 25, the diagram shows 4 pieces of lab equipment. Which pieces are used to find the density of a liquid? This is basic recall. Density is mass divided by volume. We need a balance to find the mass. We need for liquid a measuring cylinder for the volume of water. So that is B. In 26, the diagram shows an object moving at constant speed in a circular path in the direction shown. A force acts on the object to keep it in the circular path. Again, I told you that this is, although it is actually very complicated physics, for GCSE, you just have to remember that any object moving in a circle has to have a resultant force that acts towards the centre of the circle. So place a dot where the centre of the circle is, and then find the object. The arrow has to point towards that dot. You just need to remember this. It is D. In 27, a trolley of mass 4 kilograms travelling with velocity 4 metres per second collides with another trolley with half the mass and half the velocity. After the collision, it tells you that the 4 kilogram trolley is reduced to 3 metres per second. And then what is the missing value? What is the velocity here? Same process as always. The collision does not get rid of any of the momentum. It's just it changes where the momentum is. The total momentum of the system as a whole before the collision has to equal the total momentum of the system after the collision. Momentum is mass multiplied by velocity. So the momentum of trolley 1 is 4 times 4. The momentum of trolley 2 is 2 times 2. In total, I have 20 kilogram meters per second worth of momentum before the collision happens. After the collision happens, I have a mass 4 kilogram moving at 3 meters per second. So this trolley has 12 kilogram meters per second of momentum. The second one, I don't know the velocity of, but I know that its momentum is equal to 2 multiplied by its velocity. So I know that 20 must equal to 12 plus 2v because total momentum has to be conserved. I can rearrange this. 20 minus 12 must equal 2v. That's equal to 8. To get v by itself, I have to divide both sides by 2. I get 4. In question 28, a sound wave travels from air into water. Which row describes what happens to the frequency and the wavelength of the wave? So we know how sound propagates. Particles are vibrating and then they collide with a neighbouring particle. They knock and they pass on the vibration. That continues until you reach your ear or a microphone, and then you can pick up that signal. So it makes sense that when particles are closer together, the vibrations are going to be passed on more quickly. The speed of the wave travelling through space is going to increase. I haven't changed my sound source. So I'm not changing the number of waves that are passing a point per second because I'm producing the same number of waves per second. Just because I've gone from air into water, I haven't changed the frequency with which I'm sending a wave in. So, wave speed equation, V is equal to F multiplied by lambda. Velocity is equal to frequency multiplied by wavelength. If the velocity increases, but the frequency stays the same, it must mean that the wavelength also increases. And that gives me D. In 29, this is a lovely question. It's just looking at the picture and seeing which one does this represent. Waves spreading out as they pass through a gap or go around an obstacle is known as diffraction. Easy. In number 30, the diagram shows an object in front of a plane mirror. So here's the eye, here's the object. Where do we see the object inside of the mirror? You can just use your day-to-day common sense. When you look at things in the mirror, they appear in line with where they are. So they should just be directly behind the mirror, but you can also use a ray diagram like I've drawn to show how you backtrack to find that image. But you should just be picking B. In question 31, it says, which diagram shows a graph of current against voltage for a filament lamp? Now, when I taught you this, I actually gave you the negative as well. And I said that your filament lamp looks like an S shape. But you can see that you only have the positive quadrant in your diagram options. So you just need to focus in on this section. So that gets you to D. This is one that I just asked you to remember. If you absolutely can't remember, you can use the equation. We know that when a lamp gets hot, its resistance will increase. A lamp is going to get hotter if the voltage increases. Okay, we know that the gradient of this graph is I divided by V. That is equal to 1 divided by R from our equation. So it makes sense that if V is increasing, the gradient should decrease. Okay, but really you should just be able to remember this one. Okay. In 32, the diagrams show speed-time graphs for 4 different bodies moving for 6 seconds. Which body travelled the least distance? Well, distance is speed times time, so it's the area under the graph. So in each case, you can pause and have a look. I have literally calculated the area of the triangles under the graph or the rectangles, and you will see that the least distance is B. It is 20 metres. In 33, the pressure of a fixed mass of gas in a cylinder is measured. The volume of the gas in the cylinder is slowly decreased. The temperature of the gas does not change. We know that when the temperature of a gas does not change, PV is constant. P1V1 equals P2V2 when temperature is constant. This was an equation you were given. Okay, so which graph shows how the pressure of the gas changes during this process? Well, if V decreases, P must increase to keep the multiplication of the two constant. Okay, so if I draw it like this, P times V, if V gets smaller, P has to get bigger so that when you multiply them together, you get the same value. So we know that it has to be either B or C. The pressure has to be increasing. Okay, it also makes sense if we're making the volume smaller, we're going to have more collisions in a same area because there's now less area for the total particles to be in. So the only thing then is to notice that this one starts from the origin, which implies that there is a point in time where the gas has no pressure. That means that you're at absolute zero. That's a theoretical value where the gas molecules have no kinetic energy. We can approach that, but we don't have any evidence to see that has ever happened. It also certainly won't happen on Earth. That's a ridiculously cold temperature that would need to be in order to have a gas at absolute zero. So we do have some starting pressure, so that gets us C. In 34, thorium-230 is represented by this symbol. This was done shockingly badly. This is chemistry. You should be really familiar with this. It's radioactive and it emits alpha particles. Step 1 is to remember that an alpha particle is a helium nucleus, 2 protons plus 2 neutrons. So, if thorium decays by emitting alpha, it has to produce an element that's now smaller. And we know that we conserve our numbers on the top and the bottom of the equation. So if we have 230 before the decay, 4 of which go off as an alpha particle on the top, this number has to be 230 minus 4. And then on the bottom, we had 2 protons, 90 originally, 90 minus 2 is 88, gives me A. In 35, a ray of light is shone onto the surface of a mirror. Again, you just need to remember that angles are measured relative to the normal line. So we're looking at 2 and 3 for angle of incidence and angle of reflection. You either know it or you don't. In 36, a lamp rated 12 volts, 2 amps is switched on for 1 minute. Automatically write to yourself that that is 60 seconds. How much energy is transferred by the lamp? Energy transferred is power in joules per second multiplied by time. Power can be found by current multiplied by voltage, P equals IV, poison IV. So energy transferred is equal to IVT. The current was 2, the voltage was 12, the time was 60, gets you to answer D. In 37, a fixed mass of gas is trapped in a container. The temperature of the gas is increased, so the average kinetic energy of the molecules is going to get greater. They're going to be moving with more velocity. There will be more collisions happening than previous. The volume has been kept constant. This means that if you have more collisions in the same volume, you must have a higher pressure. Higher temperature, higher pressure, we know this. So if temperature goes up, pressure goes up. So we're looking at A or D to begin with. It says, how does this change affect the average kinetic energy of the molecules? Well, if temperature increases, we know that temperature is a measure of the average kinetic energy of the molecules. That's the definition of temperature. If the temperature has increased, it must mean that the average kinetic energy of the particles has also increased. This was kind of a memory one as well, to be honest. There's not much more to it than that. Last page, finally, 38. 4 thermometers with their bulbs painted different colours are placed at equal distances from a radiant heater. Which thermometer shows the slowest temperature rise? So we don't want as much energy being absorbed per second when the heater is first switched on. So we want the worst absorber. We know that the best absorbers are dark and matte. We need shiny and light to be good at reflecting, but very bad at absorbing. When you're bad at absorbing, you don't take that energy in. The kinetic energy of the particles isn't going to change. It's not going to have a temperature rise. So we want shiny white. 39. A truck is towing a car along a straight horizontal road at a constant speed. Again, this tells us constant speed, no acceleration, means no resultant force. So initially, the forces are balanced. The rope breaks. Which row gives the direction of the initial acceleration of the truck? So that's the key. We're focusing in on the truck and not the car. After the rope breaks. And what is the reason? So, for the truck moving at constant speed, it provides a driving force. The person in the truck puts their foot on the gas pedal. Driving force, pushing forward. There have to be forces acting back against that so that it moves at a constant speed rather than accelerates. So therefore, the tension in the rope, because the car is going to be pulling back on the truck, plus any air resistance, these two must add up to equal the driving force, so that initially the overall force on the truck is 0 newtons. Now, if the rope suddenly breaks, the tension force disappears. So suddenly what's left is the driving force and the resistive air resistance friction forces. It must be that if initially the driving force was the sum of these two and then this one disappears, the driving force is now going to be bigger than the resistive forces. So all of a sudden the truck is going to be able to accelerate to the right, the driving force is larger. So therefore the truck is going to move off to the right and the driving force is going to be greater. The answer is C. Last but not least, which change occurs in the nucleus of a radioactive atom during beta emission? Firstly, if you've forgotten that beta is an electron, you're not going to be able to do this. We know that inside of a nucleus, in beta decay, a neutron is converting itself into a proton and an electron. Together they're neutral. The proton remains in the atom's nucleus. The electron is given off. Okay, and so the answer is A.